Today we discuss the topic of conduction mechanism in conductors. Okay, this is a very important derivation for class 12th. In this we will learn that how do electrons actually carry current from one place to another, or from one device to another, or how electrons actually move from negative terminal to the positive terminal in a circuit. Okay, so first we need to understand is what are free electrons. See, every metal has got many electrons inside it. Most of these electrons are inside the atom, while a few of these electrons are on the outer parts of the atom. And these electrons, the outer electrons, they play a role in chemical bonding. Now, some of these outer electrons, due to a slight high temperature or due to even very small amount of heat, these electrons have enough energy. They gain enough energy and they simply move out. They become free from the vicinity of atom. That means they do not belong to any atom. They do not belong to any bond, but they keep on moving around or inside a conductor. They will not leave the surface of conductor, but they will keep on moving inside it. And these electrons are known as free electrons. Now, in good conductors, their number is very high. The number is about 10 to the power 23 per meter cube. So now the question arises that if so many electrons are moving inside a conductor, if I put an ammeter across it, because the electrons are moving, current has to be there. So is there any current due to motion or random motion of these free electrons? The answer is no, there is no current due to the movement of free electrons. And why it is so? Because see, as many number of electrons are going from right to left, so many will be going from left to right. As many go from bottom to top, so many go from top to bottom. So the number of electrons going one way is same as the number of electrons going the opposite way. So the net charge flowing through any cross-sectional area becomes zero, and hence the current becomes zero. Okay. Now, please remember that the movement of these free electrons is due to heat. Okay, and the speed with which these free electrons achieve due to heat is known as their thermal speed. Okay, let us find out the average thermal speed of these free electrons. Let us write the very basic equations of classical mechanics for these electrons. Only in the presence of heat. There is no potential difference applied, there is no battery attached to it. Okay. Now, as I told you, if 100 electrons move from left to right, 100 electrons move from right to left. If 200 electrons go upward, 200 electrons, same number of electrons will be going downwards. So the average velocity of these electrons will be equal to what? Equal to 0. If I have n number of electrons, n number of free electrons in a conductor, then their velocity vectors will be written as u1, u2, u3, u4, u5, u6, u7 up to un. And when I take the average velocity, not speed, average velocity, what I will have to do? I will have to add them u1 plus u2 plus u3 and all the additions up to un, and then I have to divide it by the total number of electrons, that is n. Now this average velocity will be equal to 0. Why this will be equal to 0? Because half of these u's, these initial velocities, they will have positive sign, and the remaining half of these velocities, because they are moving in opposite direction, they will have negative signs, and this average comes out to be 0. Now what happens if a potential difference gets applied to this conductor. Let us see. I'm showing you the cross-sectional area of a conductor, the same conductor which we have discussed above. Now this conductor is given some potential difference on both its sides. Suppose on this side I have given it a positive potential, on the other side I have given it a negative potential. Okay, and this is the path of electron. The electron first goes like this, then it collides with some atom and then again changes its path. Here it again collides and again changes its path. And suppose in time t, it starts from this point and it ends its motion at this point. During time t, it has reached this. Now this is what? This is the path of electron when the potential difference is not applied. Now, if the potential difference gets applied, what will happen to the path of this electron? Okay. Now, electrons have a tendency to get attracted towards a positive charge, to get attracted towards a positive potential. So, what this positive potential is going to do, it is going to drag the electron towards this side. It is going to drag the electron towards this side. Okay, and it is going to change the path of electron only by a small amount like this. It has collided this at this point in absence of potential. In presence of potential, there is a small attraction on this, and this will collide here a little towards positive side. Second collision was taking place over here. Now the second collision will be here. And during the same time t, when the electron was reaching this point, it will not be able to reach this point, but it will be able to reach a point which is a little towards the positive side. Okay. Now consider another electron. In absence of these potentials, first the electron moved this way, it collided, then it came this way, okay, and again collided and it came this way. Okay, this was all due to heat. Now if we apply potentials, negative towards this side, positive towards this side, we know that this electron is going to be pulled a little bit towards the positive side, and its this path is going to change a little bit. It will be obviously attracted towards this. So uh, during the same time t, it will be moving a little ahead. Why? Because of the attraction. Again, it will be colliding the second time a little ahead of the first time, and it is going to end its motion again at a point which is a little towards the positive side. Okay, so can you see that whether the electron is going from left to right, the effect of positive potential and negative potential is that the electron, the ending point, the terminal point of electron is shifted towards this. Even if the electron was going from right to left, what is the effect on the motion of electron? Again, the terminal point of this electron has shifted a little towards this. So irrespective of the movement of electron, the small change in the path of electron, very small change in the path of electron, is a little towards the positive side. Okay, now this small, very small displacements are the actual cause of electric current. We have been learning that motion of electron is current, motion of electron is current, but now you know it is not the motion of electron which is responsible for electric currents, but these small displacements for electrons, they are actually responsible for electric current. Okay, so this is the cause of electric current, and now a very small conceptual part, that the path of electron is changing. So whenever the path of something changes, what do we call it? We call it what? Displacement. Okay, so these are the displacements of electron caused in the presence of potential difference. And now, coming to one more fact. In the first unit of electrostats, we have learned that electric field inside a conductor is always equals to 0. But that was only in static conditions. This was not supposed to be there in any dynamic condition. In dynamic condition, that means when the motion is taking place for electrons, electric field is not equal to 0. That means it is having some finite value. What happens? This happens. See, this is positive potential, this is negative potential. That means here we have a collection of positive charges. Here on the negative side we have collection of negative charges. Electric field starts from positive, goes towards negative. So there are many electric field lines inside the conductor, and again, because there are electric field lines, there is an electric field inside a conductor, but that is happening only if the potential difference gets applied. Okay?